Everyone, welcome back to my channel. So today I'll be going through P6 Science Prelim 2024 Tao Nan paper. So over here we have four identical magnet with the same magnetic strength, okay, and two different springs, okay, R and S of equal original length, and are being used in this setup. So we take a look at this setup. We have the magnet that's sitting onto the spring. So the spring is being compressed, and we have the similar setup on diagram 2. But the only thing that's different is that the repelling distance are different. Okay, so they have different repelling distance. Okay, repelling distance, they are different, and there are certain things that we can pick it up as well. Okay, for example, this. It seems that if they have the original length, oh no, not if they have the original length, and you can see that S is compressed more. So in this case, it might be less stiff, than S. Okay, might be. Okay, so then this one is compressed less. Okay, this might be stiffer. Okay, and if we take a look at this two part, right? Since the magnet have the same magnetic strength, does that mean the repelling force they are the same? In fact, no, the repelling force, they are different because of the repelling distance being different. So in this case, let's go back to this idea of magnetic force. Okay, magnetic force is actually the push or pull between magnet. It depends on both the strength as well as the distance. So the strength is the same, right? We can kind of ignore it, but the distance, they are different. Okay, so you can see that the closer they are, the stronger the push between them, the repulsive push. So in this case, right, we can kind of say that for diagram 2, right, the magnetic force of repulsion is way stronger than diagram 1 because they are closer together. They are closer, so the magnetic force of repulsion should be stronger. So let me just draw this part. The magnetic force of repulsion is kind of indeed weaker in diagram 1. So okay, then the magnetic force of repulsion is indeed stronger in diagram 2. Okay, magnetic force of repulsion. So can you see that I draw a smaller set of arrow to indicate the strength of the repulsion? I draw a longer arrow to indicate that this part is stronger for diagram 2. So I'm trying to say that this is stronger. Okay, so in this case, the amount of repulsion, right, that's acting on both magnet, they are different. One of them is stronger, diagram 2 is stronger, diagram 1 is weaker. Okay, and what are some other forces that could have appeared over here? The gravitational force acting on the magnet, they are kind of the same because I can say that they are the same identical magnet. So in this case, the weight of the magnet, right, should be the same. Okay, I can take it as that, so I can kind of cancel them off. Okay, I can kind of ignore them, but I have to take note that these are the forces that could have been played. Okay, so we have the gravitational force acting on the magnet. Okay, acting on magnet. Okay, we have the magnetic force of repulsion, which are different. Okay, different. We also have the elastic spring force. Okay, exerted by S and R onto magnet. Okay, so this is in the upward direction, while the magnetic force of repulsion should be in the downward direction. Okay, so the magnetic force is in downward, right? Then the elastic spring force is in the upward because the spring wants to return back to its original length. Okay, so it will try to push it up in this case. Okay, so in this case, right, since we see that the object here, right, is not moving, okay, is kind of in place, we can say that the upward force should be equal to the downward force. That means the elastic spring force should be equal to the magnetic force of repulsion. That's why the object kind of remain there, that's unmoved. Okay, so in this case, if the arrow is if this set of arrow is only in this length, okay, then the downward arrow should be in the same length. Okay, this will represent the elastic spring force acting on the magnet Okay, in this case, so they are of the same. Okay, so the other set will be more or less in the same method. Okay, the object is not moving, so the elastic spring force should be equal to the magnetic force of repulsion, as well as there's another component which is the gravitational force that's acting downward. But we're going to kind of remove them because they are the same. Okay, but we are going to consider what is different only, which is the magnetic force of repulsion. Okay, so in this case, right, the magnetic force of repulsion is equal to the elastic spring force in diagram 2, right? So if I draw this set of arrow being longer, okay, the upward arrow should also be longer to counter them. Okay, so this is elastic spring force. So can you see that what I'm trying to do is that I'm trying to say that the elastic spring force, they are kind of different because of the magnetic force of repulsion that is different, okay, due to the distance that is being shown over here, while the magnetic force, the magnetic strength are the same. Okay? They have the same magnetic strength, but because the distance is different, so the downward force, right, should be different for the both of them. The shorter distance will have a stronger downward force. Therefore, in order to balance the magnetic upwards, right, the elastic spring force exerted by the spring should be way stronger for the one with the shorter length. Okay, so in this case, right, what could be the answer? Okay, the answer is 2. Okay, spring R exert a larger elastic spring force, okay, than S. Okay, the answer is 2 in this case, because over here we see that the upward arrow, okay, the upward arrow over here is way longer than the upward arrow over here. So 2 is correct. Okay, so let's go through why the rest are wrong. Okay, so spring S is stiffer. In this case, as I say that we can kind of see that it's being compressed more with less force that is acting on it. So in this case, spring S should be the one that is less stiff. Okay, should be the less stiff. Less stiff spring. So in this case, this is a wrong statement, and the length of compression of S is definitely 10. This is also wrong. That means how much the spring is compressed is not 10. We just don't have the information. So this question is just trying to throw your card. In this case, the repelling distance is 10 doesn't mean that the compression over here is 10 cm. It doesn't mean this. This is a wrong statement. So basically, we just we don't really have this information to tell. That's why we cannot make this conclusion. 1 and 3 is wrong. 4, it's one of those options that some of y'all might choose, but this is also wrong. It's because of the repelling distance. Some may be tricked by this term, the same magnetic strength. Some may be tricked by this. So same magnetic strength, the force must be the same, right? So therefore, the upward force by the spring should be the same, even though they are compressed to different extent, because they already tell you it's different spring. The stiffness should be different. But in this case, 4 is wrong because the repelling distance is different. Therefore, the downward or repulsive force should be different. So the upward elastic spring force exerted by both springs should be different to ensure that the magnet is kept in balance. So that's why 4 is wrong. So to really conclude this, right? To really conclude this is that the argument for 4 seems logical, but it makes a very critical mistake because it tries to assume that the only downward force is the magnet weight. And if that will be the case, right, the downward force will be the same in both pictures, which means the spring upward force will also be the same. But this is wrong because we forget about, if you have choose 4, you have forget about the repulsive force, which is the downward push by the repulsion due to the light poles that are facing each other. Therefore, this force changes with distance. Since the distance is closer, the downward force for diagram 2 is much larger. So in order to balance the magnet on that spring, the upward force must be larger in order for it to balance in this case. So in this case, the total downward force is different in each picture. So the elastic spring force should be different. So how do you really answer for part 2? So this is some of the logical steps that I've put forth. So you can compare, you can identify all the downward force. The spring force must be balanced, must balance everything pushing on it down. not just the weight, not just the gravitational force acting on a magnet, but also the repulsive force. Okay, so and you have to be careful about the term magnetic force versus magnetic strength. Okay, strength is the same, doesn't mean that force are the same. Okay, you have to depend on the distance as well. The last is you compare between the distance. Okay, the first one show you, or diagram one show you 10 cm, 10 centimeter, so weaker. Okay, the other one show you, which is diagram 2, 5 cm stronger. So therefore, since the repulsive push is much stronger in the second diagram, so the total downward force on spring R is greater than the total downward force on spring S. Therefore, to stay in the balance, right, R must push up with a larger elastic spring force. Okay, even though the compression is way lesser, but because they already tell you that they are different spring, the stiffness is different, so you cannot depend on the compression as a way to as a way of answer. Because some of you may think that if the spring are compressed more, they should have more elastic spring force acting upwards, but no. Okay, in this case it doesn't work, because the stiffness of the spring, they are very different. Okay, so in this case, to conclude, right, 2 is the correct answer. Okay, not 4. And when is 4 the correct answer? 4 is correct. 4 can be the correct answer if I remove this. I remove the top part of the magnet. I remove the top part of the magnet, then the spring S and R will exert the same amount of elastic spring force. Because the only force that is concerned at that point of time, right, if you remove these two parts, right, will be only the weight of the magnet that is pushing onto the spring down. And then since both of them they are identical, they should have the same weight. So even though their compression might be different due to the different stiffness, right, they should have the same amount of elastic spring force acting, pushing it up. So in actual fact, this may look something like this. Okay, this may look something like this. Let me just draw it over here. Okay. Okay, so this is R, this is S. No, sorry, this is S, this is R. Okay, even though S is more compressed, but because there is nothing acting, nothing pushing it down, right? So the amount of gravitational force acting on the magnet for both should be the same. Okay, should be the same. Okay, because they have the same, so they must balance it with the same amount of elastic spring force that's pushing it out. Then in this case, right, if you don't have the top two magnet that is repelling them, right, then 4 is the correct answer. Okay, for this part. So this is a pretty difficult question because you involve 3 types of forces together, even though one of them you don't need to consider, which is the gravitational force acting on the magnet, because both of them they have the same identical magnet. So in this case, right, so this is why 4 is 2 is the correct answer. So let me just put it here. Okay, this is a very difficult question because there's a lot of things for you to consider. Okay, with that, thank you very much.